In physics, thermal conductivity is the property of a material to conduct heat. It is evaluated primarily in terms of Fourier's law for heat conduction. Heat transfer occurs at a lower rate across materials of low thermal conductivity than across materials of high thermal conductivity. Correspondingly, materials of high thermal conductivity are widely used in heat sink applications, and materials of low thermal conductivity are used as thermal insulation. The thermal conductivity of a material may depend on temperature. The reciprocal of thermal conductivity is called thermal resistivity. Thermal conductivity is actually a tensor, which means it is possible to have different values in different directions. See #thermal anisotropy below. Units of thermal conductivity. In SI units, thermal conductivity is measured in watts per meter Kelvin. The dimension of thermal conductivity is m1 L1 T-3 θ-1. These variables are mass, length, time, and temperature. In imperial units, thermal conductivity is measured in BTU. Other units which are closely related to the thermal conductivity are in common use in the construction and textile industries. The construction industry makes use of units such as the R value and the U value. Although related to the thermal conductivity of a material used in an insulation product, R and U values are dependent on the thickness of the product. Likewise, the textile industry has several units including the TOG and the CLO, which express thermal resistance of a material in a way analogous to the R values used in the construction industry. Measurement. There are a number of ways to measure thermal conductivity. Each of these is suitable for a limited range of materials, depending on the thermal properties and the medium temperature. There is a distinction between steady-state and transient techniques. In general, steady-state techniques are useful when the temperature of the material does not change with time. This makes the signal analysis straightforward. The disadvantage is that a well-engineered experimental setup is usually needed. The divided bar is the most common device used for consolidated rock solids. Experimental values. Thermal conductivity is important in material science, research, electronics, building insulation and related fields, especially where high operating temperatures are achieved. Several materials are shown in the list of thermal conductivities. These should be considered approximate due to the uncertainties related to material definitions. High energy generation rates within electronics or turbines require the use of materials with high thermal conductivity such as copper, aluminium, and silver. On the other hand, materials with low thermal conductance, such as polystyrene and alumina, are used in building construction or in furnaces in an effort to slow the flow of heat, i.e., for insulation purposes. Definitions. The reciprocal of thermal conductivity is thermal resistivity, usually expressed in Kelvin meters per watt. For a given thickness of a material, that particular construction's thermal resistance and the reciprocal property, thermal conductance, can be calculated. Unfortunately, there are differing definitions for these terms. Thermal conductivity, K, often depends on temperature. Therefore, the definitions listed below make sense when the thermal conductivity is temperature independent. Otherwise, an representative mean value has to be considered. For more, see the equations section below. Conductance for general scientific use. Thermal conductance is the quantity of heat that passes in unit time through a plate of particular area and thickness when its opposite faces differ in temperature by 1 Kelvin. For a plate of thermal conductivity K, area A and thickness L, the conductance calculated is Ca, L, measured in Wk-1. The thermal conductance of that particular construction is the inverse of the thermal resistance. Thermal conductivity and conductance are analogous to electrical conductivity and electrical conductance. There is also a measure known as heat transfer coefficient, the quantity of heat that passes in unit time through a unit area of a plate of particular thickness when its opposite faces differ in temperature by 1 Kelvin. The reciprocal is thermal insulance. In summary, thermal conductance equals Ca L measured in Wk-1, thermal resistance equals L measured in Kw-1, heat transfer coefficient equals K L measured in Wk-1 m-2, thermal insulance equals L K measured in Km2W-1. The heat transfer coefficient is also known as thermal admittance in the sense that the material may be seen as admitting heat to flow. Resistance. Thermal resistance is the ability of a material to resist the flow of heat. Thermal resistance is the reciprocal of thermal conductance, i.e., lowering its value will raise the heat conduction and vice versa. When thermal resistances occur in series, they are additive. Thus, when heat flows consecutively through two components each with a resistance of 3 degrees Celsius, W, the total resistance is 3 plus 3 equals 6 degrees Celsius, W. A common engineering design problem involves the selection of an appropriate sized heat sink for a given heat source. Working in units of thermal resistance greatly simplifies the design calculation. The following formula can be used to estimate the performance, where RHS is the maximum thermal resistance of the heat sink to ambient, in degree C, W. Delta T is the required temperature difference, in degree C. PTH is the thermal power, in watts. Rs is the thermal resistance of the heat source, in degree C, W. For example, if a component produces 100 W of heat, and has a thermal resistance of 0.5 degrees Celsius, W, what is the maximum thermal resistance of the heat sink? Suppose the maximum temperature is 125 degrees Celsius, and the ambient temperature is 25 degrees Celsius, then delta T is 100 degrees Celsius. The heat sink's thermal resistance to ambient must then be 0.5 degrees Celsius, W or less. Transmittance. A third term, thermal transmittance, quantifies the thermal conductance of a structure along with heat transfer due to convection and radiation. It is measured in the same units as thermal conductance and is sometimes known as the composite thermal conductance. The term U value is often used. Admittance. The thermal admittance of a material, such as a building fabric, is a measure of the ability of a material to transfer heat in the presence of a temperature difference on opposite sides of the material. Thermal admittance is measured in the same units as a heat transfer coefficient, power per unit area per temperature change. Thermal admittance of a building fabric affects a building's thermal response to variation in outside temperature. Influencing factors. Temperature. The effect of temperature on thermal conductivity is different for metals and non-metals. In metals, conductivity is primarily due to free electrons. Following the Wiedemann-Franz law, thermal conductivity of metals is approximately proportional to the absolute temperature times electrical conductivity. In pure metals, the electrical conductivity decreases with increasing temperature and thus the product of the two, the thermal conductivity, stays approximately constant. In alloys, the change in electrical conductivity is usually smaller and thus thermal conductivity increases with temperature, often proportionally to temperature. On the other hand, heat conductivity in non-metals is mainly due to lattice vibrations. Except for high-quality crystals at low temperatures, the phonon mean free path is not reduced significantly at higher temperatures. Thus, the thermal conductivity of non-metals is approximately constant at high temperatures. At low temperatures well below the Debye temperature, thermal conductivity decreases, as does the heat capacity. Chemical phase. When a material undergoes a phase change from solid to liquid or from liquid to gas, the thermal conductivity may change. An example of this would be the change in thermal conductivity that occurs when ice at 0 degrees Celsius melts to form liquid water at 0 degrees Celsius. Thermal anisotropy. Some substances, such as non-cubic crystals, can exhibit different thermal conductivities along different crystal axes. Due to differences in phonon coupling along a given crystal axis, Sapphire is a notable example of variable thermal conductivity based on orientation and temperature, with 35 with along the C-axis and 32 with along the A-axis. Wood generally conducts better along the grain than across it. When anisotropy is present, the direction of heat flow may not be exactly the same as the direction of the thermal gradient. Electrical conductivity in metals. Thermal conductivity approximately tracks electrical conductivity according to the Wiedemann and Franz law. As freely moving valence electrons transfer not only electric current but also heat energy. However, the general correlation between electrical and thermal conductance does not hold for other materials, due to the increased importance of phonon carriers for heat in non-metals. Highly electrically conductive silver is less thermally conductive than diamond, which is an electrical insulator, but due to its orderly array of atoms it is conductive of heat via phonons. Magnetic field. The influence of magnetic fields on thermal conductivity is known as the Rigi-Leduc effect. Convection air and other gases are generally good insulators, in the absence of convection. Therefore, many insulating materials function simply by having a large number of gas-filled pockets which prevent large-scale convection. Examples of these include expanded and extruded polystyrene and silica aerogel, as well as warm clothes. Natural, biological insulators such as fur and feathers achieve similar effects by dramatically inhibiting convection of air or water near an animal's skin. Light gases, such as hydrogen and helium, typically have high thermal conductivity. Dense gases such as xenon and dichlorodiafluoromethane have low thermal conductivity. An exception, sulfur hexafluoride, a dense gas, has a relatively high thermal conductivity due to its high heat capacity. Argon, a gas denser than air, is often used in insulated glazing to improve their insulation characteristics.